Hello? Wow. No. Okay. Tests for divergence, property series of positive terms, and integral tests. This is really good. We're going to make it all, I'm going to try and make it all the way through the P series in the notes today. So I'm going to do my best to get that far. All right, theorem. Infinite series as k equals 1 to infinity of a of k, the series converges, then the limit as n goes to infinity should be 0, right? As the limit, it should go to 0, right? Yes, I'm testing for that. So in words, if this right here converges, then this equals 0. Okay, now the contrapositive. Okay? The converse of this. It would be if the limit as n goes to infinity, a of n equals 0, then the series may converge or diverge. Okay, here's an analogy. Okay? All thumbs are fingers, but not all fingers are thumbs. Right?
Yeah, that makes sense.
Okay, all thumbs are fingers, right? All thumbs are fingers, but not all fingers are thumbs.
All squares are rectangles, but not all rectangles are squares.
Okay. Or let's say all dolphins are mammals, but not all mammals are dolphins. Anyway, all right. So that's what it means. So you can't work it the other way, because other way it's going to converge or diverge. Right. This is as the series converges, it goes to 0. But just because right here I'm saying this, it's going to go either way. So I can't start with the limit. All right. So theorem we obtained useful test for divergence. The theorem for test for divergence is the infinite series diverges if this does not go to 0. Okay. All right, so as the series goes, so this is going to be 87 does not equal 0. So therefore, this is going to diverge. Straightforward, right? Okay, what about this one? Yeah, because this would be the limit, right? Limit as n goes to infinity of n, which is just infinity, right? So that one right there is not equal to 0, so therefore that is divergent. All right, what about this next one?
Yeah, wouldn't it just bounce back?
Okay, so which one's this? What would I call this one?
Yeah,
Alternating. Alternating. So it's alternating. It's jumping up and down like this, right, to the same spot. Okay, same spot. So this one, it would be basically, so it's a limit as n goes to infinity, and it's going to be basically a piecewise function where n is odd, and n is even, right? Yeah? So it's going to change according to that. So it's going to bounce in between. So I'm not going to get a limit off of that. All right, so what about this one right here? Okay, so now this is going to be, let's see, the limit as n goes to infinity of 2 to the n. What are we going to get there? Okay, so this one's going to go to infinity, right?
Yeah.
So therefore that one is not equal to 0. Yep. That's why these are all the divergent tests. All right. If two infinite series are identical after a certain term, that means that it's going to be the same thing further down the road. Okay, then either both series converge or both series diverge. If both series converge, they do not necessarily have the same sum. Okay, it doesn't mean that they're going to have the same sum. Okay, theorem, sum and difference, convergent series. So if the sum of this is equal to S and the sum of this is equal to T, okay, that means that both of these, S is convergent and T is also convergent, are two convergent series in the series of this, both these together, the series, okay, will also converge. So if these two pieces individually converge, then the addition and subtraction of those two will also converge. Okay. It's like rational numbers. Do you guys know what a rational number is? Okay, yeah. Okay, so I have fractions, right? The numbers I get illustrate by using a fraction, right? Okay, so if I add two rational numbers, I'll always get another rational number. Okay? So if I subtract two rational numbers, I'll also get a rational number. But if I put an irrational number in either one of those, no matter what, my answer has to be irrational. Okay? Irrational is a number I cannot represent as a fraction. Okay? It's going to be repeating decimals that go on forever. Non-repeating decimals that go on forever. Okay? So that's an irrational. So as soon as I throw one of those into the mix, then it's going to be. So if it was two irrationals, guess what? It's still going to be irrational. So therefore, if it's two divergent, then they are still going to diverge. Okay. All right. Constant multiples is a series. So C be a non-zero real number. S is the convergent of the series. Then C times the convergent also converge. So it's the multiplier. So that's C in this case is going to represent some constant coefficient. The coefficient. Remember we're having that issue with the K and the C yesterday. So if the series diverges, then the series also diverges if I'm multiplying by C. Multiplying each terms by non-zero constant does not affect the convergence or divergence of the series. Okay, so this thing right here. Determine whether that these are going to converge or diverge. Now, in this case right here, I'm going to have at K equals 4. So what does that mean if K equals 4? What are my numbers going to look like?
Or go and start at
1/4 plus.
Yeah, you're just starting at 4, right?
Yeah. Yeah, so it's going to be like that, right?
Yeah.
Okay, so what can I compare it to? Can I compare it to 1 over n?
Yeah.
Okay, so now I get to compare it to 1 over n, can I?
Yeah.
And so if I just compare it to that, then it's going to go with just writing it out as the limit as n approaches infinity of 1 over n
Equals 0. Convergent.
right?
Yeah.
So I'm comparing it because isn't 1 over n the same as this? But if it was just 1 over n, if I'm starting at 1, right? It would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, right? Hey, look, there it is. Dot, dot, dot.
Yeah.
So this goes back to the definition. If it's going to be continuous, like after a certain point that they have the same value, so therefore I could use those as a comparison, and from here, this goes to 0. So we're going to say that this one is going to converge. Uh-oh. Uh-oh. This one is not. This is going to be harmonic.
Harmonic.
Yeah. This one's a harmonic series, not the one. I have it right here. That sucks. I hate screwing up.
Define.
I just had my notes, doing my notes too.
Oh, okay.
So, like a train rider. Hobo.
The harmonic convergence.
It's too bad. I'm just talking about a hobo on a.
Oh, okay, all right.
One's playing the
So
tunes, the other one's
I will show you where I messed up at, and I'm going to show you guys.
a bluegrass band.
Open 8.2. Why did I pick 6.2?
That's alright.
Here it is.
Wow.
There it was. I was comparing it. Yeah. I had it right, but I forgot that the harmonic series diverges.
Is that in 8.2?
Yeah, it's 8.2.
Just write it.
Wait, why does the harmonic series diverge?
It's going to diverge because it's going to continuously go
Oh,
up, but it's not going to go up to a number.
Okay.
Because if you think about it carefully. Yes, as a limit goes, right? So as I do is as 1 over n, and then as n goes to infinity, that should. But that's why this is specific. You know, this is a harmonic.
Right.
That's why this is like the exception to the rule. So you're like, oh, this one's gonna be harmonic because if you keep adding a little bit on, because that's going to keep going up, up, up. It's not going to go up to a certain number. It's going to just keep going up infinity. Even though I'm going up a finite amount, or not a finite, infinite amount, as I keep going up, it's not going to go up to a single number. It's going to go up very slow. As I'm getting up closer to infinity, it's going to be super slow. But it's still going up. Does that make sense or no?
Yeah, it's like looking at it as a sum rather than.
Yes, the sum of these going up. So if I have a graph of this, here's 1 and here's 2. So at 1 I get 1. At 2 I get 1.5, right? Okay. At 3 it's going to be plus that, so it's going to be 2 and 1. There. Okay, so now it's at 4, it's going to be right here. So it's eventually going to go like this. So it's going to go up, but it's still going to keep going up and up and up. Just a little bit every time. So that's why this is the exception. This is the harmonic. I believe I screwed that one up. I'm sorry. Okay, especially all those people that made it on Friday.
Yeah.
I know. There we go. Okay, so, all right, so yeah, there's that one. That one's the harmonic. Okay, so if that one's harmonic, then therefore this one is going to diverge.
So if we see something like that, then it's automatically a harmonic.
Yes, like that one. That one will be.
How is the economy so bad? There's harmony.
I know, right? Ain't no sunshine. All right. So, what about the second one? Is this just going to be 2 times that? 2 times that harmonic?
Right, so then it's just gonna be.
Okay, so it's going to be harmonic again.
Harmonic times
Harmonic.
2.
And so therefore it's divergent. All right. Okay, so what about this one? All right, so I have the sum of 2 of them, right? Say yes.
Yes.
Okay, since I have the sum of 2 of them,
We can break it up.
break it up. So this is going to look like the sum. So I'm going to rewrite this as what? What am I going to rewrite this first one as? 1 over 2 to the
K minus.
k minus 1, right?
Oh.
Yeah?
Yep.
What is my a value here?
It's gonna be 1.
It's going to be 1, right? So I'm going to have 1 there, and then it's going to be, yep. So what is this one going to do?
Convert.
Okay, so this is going to converge to what? So it's 1 over,
2.
so it's going to be 1 over 1 minus
It's 1/2.
1/2, my r, right?
Yeah, and then when you multiply it all by 2.
Okay, so that's going to be 1/2, right? So what is this going to go to?
2.
It's going to go to 2. Okay, that's good. So now I'm going to have, let's rewrite the other one. Remember, if either one of these diverges,
It's all about.
all of it's going to be divergent, right?
Yeah.
Okay, so now let's take a look at the other one. This other one's going to be
1/3 to the k minus 1. A is 1 again, so
okay, so it's 1 again, right? So it's 1 again. I'll put that there.
1 over 1 minus 1/3.
So 1 over 1 minus 1/3.
So it's 1/2.
So this is going to be
3
3 halves
halves.
minus 1/2. Oh, not halves.
That's in the end. Oh, sorry.
3/3. Sorry,
Thirds, yeah.
3/3.
That's 2/3 to 1
So
over
2/3,
2.
1 over 2/3, so
halves.
it's 3 halves is what we were trying to say.
Yes. Yes. So I should get 2/3 in the bottom, multiply by the reciprocal.
Mhm.
So it's going to be 3 over 2, right? So, do both of these individually converge? Yes. So what can I do with their sum?
Add them.
Add them. So I'm going to get how much?
7 halves.
7 halves. We okay? General convergent test. If an infinite series of positive terms converges, if and only if its sequence of partial sums is bounded. Okay, bounded. That means what?
It's like,
Yeah, so it's only bounded above, bounded below, right? So it's going to be somewhere in between there. It's going to be bounded. Okay, the sum of each infinite series will not exceed an upper bound. We use this theorem to develop the test for convergence of series with only positive terms. The first one is the integral test. All right, so theorem, integral test. So let f be a function that's continuous, positive, non-increasing, continuous, positive, non-increasing. Okay, non-increasing. Remember, if it stays the same, okay, that's not increasing. Okay, so not decreasing, but okay. So on the interval from 1 to infinity, let a of k equals f of k for all positive integers k. Then the improper integral of 1 to infinity of f of x dx converges. Then the series converges. Okay, remember when we did this right here, we took it to what?
limit.
Limit to like b, right?
Yeah.
Okay, so limit to b. Okay, so now this other one, if the improper integral right here diverges, then the series also diverges. Okay, given at the end of the section, so yeah, you should see the end of this section. It's
Please
a hot
refer
mess.
to page.
I know. Yeah. I don't want to do it. All right. So let's take a look at this. So what are my bounds going to be? So convergent and divergent. From where to where?
1 to infinity.
1 to infinity. Okay. What else could I do?
Oh, check if it's.
Okay. So I could do this for f of k, where this is going to be just an f of x, right?
Yeah.
So this is going to turn into what? What can I do with that 4?
Put in
Put
front.
outside. Yeah.
And this is going to be 1 over x squared plus 1 dx integral test. Integral test is going to be from 1 to b, right?
Yep.
Because I'm going to be taking the limit as b goes to infinity.
Yep. At the end there.
Okay, so it's going to be of x squared plus 1 dx. So what is 1 over x squared plus 1?
Natural log of x squared plus 1? Or
Arc tangent.
Oh, dude.
Arc tangent, right?
Yeah.
Okay.
Yeah, you're right.
All right. Well, I keep trying to prompt you guys. These things are coming up more and more and more. These are just things that you have to be able to spit out. Good job. Here's something not to spit out.
Nice catch.
I made homemade beef jerky.
Eat it, don't you?
You don't have to if you don't want.
Now he wants to spit it out.
Okay, now he wants to spit it out. Okay, anyway. All right, so this is going to give me 4 arctangent of x, right? From 1 to b. Yes? Okay, so now it's going to be top minus bottom, right? So it's the limit as x goes to,
Or B.
no, b goes to infinity, thank you. As b goes to infinity of 4 arc tangent of,
Ran out of ink.
I know,
Crack open a new box.
right? Minus,
4 arc tangent, which is
so 4 arctan of 1. Yes?
yeah.
All right, so mathematically, arctangent, now I need you guys really do this. So I want you guys all right now, okay? This is a helpful trick. All right, close your eyes. Okay, imagine the unit circle because we've gone over it so much. Picture it. Okay, picture it very clearly. So I need tangent. So on my unit circle, tangent to be positive. Where is tangent going to be a positive 1? It's a positive sine over cosine. Where is it that tangent is going to have the same value on sine as it is on cosine? Pi over 4, right?
Can it also be a negative one too?
It would be, but for this one, because the interval for the arctangent is only between negative pi over 2 to positive pi over 2. So it will, in multiples of that, it will continually repeat. Okay, because I'm talking about the inverse of it. So instead of actually just talking about my x values, you know how, you know the shape of a tangent, right? It does a little wah, right? And when it does that wah. Now, but think of the arc. The inverse means it's no longer going wah, it's going sideways now. It's now a sideways wah, okay? So it's a sideways wah, and it's actually bounded in between 2 places. So every time in between negative pi over 4 and pi over 4, I'm sorry, negative pi over 2 to positive pi over 2, it's going to make another one of those. Okay, make a little whoopee thing. Wah. Okay. So, so now you guys pictured it, right? You guys pictured it. So now let's take a look. So from here, this is going to give me what value? So where's it 1? Pi over 4, right?
Mm-hmm.
So it's pi over 4 times 4, which is pi. Okay. Now, the next one. So, as we're doing it, remember, the inverse, as b goes to infinity, now think about it. As it goes to infinity, it's going up, right? So what is that little whir stuck in between? It starts on the bottom at negative pi over 4, and think of the graph, and it goes up to positive at pi over 2, right? I'm sorry, negative pi over 2 to positive pi over 2.
Yeah.
So it's sandwiched in between there and there, right? So as it goes to infinity, it gets closer and closer to what? I'm going to show you guys a page. So my graph should look like this. Okay, so here's my negative pi over 2, and here's my positive pi over 2. So it's going to go like this. So it's going to go so as it's going to infinity, like that, it's going to go to be pi over 2. If it was going to negative infinity, negative pi over 2. All right? All right, so now this is going to be pi over 2. Did I lose it? Oh, there it is. Okay, so now I have my pi over 2, right? So I have pi over 2. This is going to be pi over 2. Pi over 2 times 4. 2 pi. 2 pi. So 2 pi minus pi gives me 1 pi. So, therefore, because of this, it is going to it's going to converge, right?
Great.
Okay, it's going to converge. From there, it's going to converge. So, with the integral test, it is going to converge. The improper integral here converges, the series converges. Right here, if the improper diverges, series diverges. So that one converged to pi, so therefore it is going to be, okay, right here. That's going to be convergent. Now, this last thing before, because I'm going to cut you off a little bit earlier today. All right, I wasn't going to make the last one. So the fact that this one goes to pi does not mean that the sum, okay, the sum is something else that we're asking for, of the series is pi. Okay? Do not confuse the value of the improper integral with the sum of the series. Okay, sum of the series is this. Right?
Oh, yeah.
Where the improper integral, 1 to infinity, is different. This gives me my sum. Ah, my markers. This gives me a sum. This is the area under. This right here is convergence or divergence.
Like a specific.
Does that make more sense now?
Yeah.
Because we're using this tool here to figure out if it's going to converge. But it doesn't mean it's a sum. We started off with something different. We turned it to this because if you notice, it's no longer the k's anymore, right? It's not the k's. It's not the n's. We turned it to the x's, which refers to an area under a curve, but it's not going to be because I started with the sum. Yes?
Yep.
Okay, good. All right, so yes, I was going to leave off with that. I'm doing this one tomorrow. All right, I want to give you guys time. Like, share, and subscribe. Hit that notification button for all those people not here just because you turned 18.